Hello world! Today I will use the ADC peripheral to read analog values from a potentiometer. I'll use the STM32F030 microcontroller for this task. I will solder the potentiometer pins to the MCU pins. Then I will generate HAL code using CubeMX. Finally, I will use HAL functions to read the data. I will observe the converted analog values. We will read the ADC using the polling method first, and then we will read multiple channels using the DMA method as well. I'm opening Start menu and clicking on STM32CubeMX to open the code generator. Click on File and then New Project to open a new project. I'm using STM32F0308 Discovery Kit, so I search STM32F030R in the commercial part number in the left tab. Here I found my Discovery Kit. I click on this one and then Start Project button. I do not want to initialize all peripherals with their default mode, so I click No. We need to configure some settings in Pinout and Configuration tab. This Discovery Kit that I'm using has an external resonator. Click RCC, then select Crystal Ceramic Resonator for high-speed clock. Next, click Sys and enable Debug Serial Wire for debugging purposes. Last, we need to select our ADC pin. Click ADC, then enable In1. You can do the same thing from Pinout View too. Click PA1, then select ADC In1. For the ADC parameter settings, select Asynchronous Clock Mode, 12-bit resolution, and Continuous Conversion Mode enabled. If you choose Asynchronous clock mode, the ADC typically clocked from HSI, internal 8 MHz RC oscillator. This is useful if you want to avoid any jitter or instability. If we select a 12-bit resolution, we will get a digital range from 0 to 4095, which is 2 to the power of 12 minus 1. For a 10-bit resolution, the digital range is from 0 to 1023. Therefore, unless there are specific reasons to use a lower resolution, it is generally better to aim for a higher resolution. Next, in the Clock Configuration tab, I enable HSE for the external resonator and set the clock signal to 48 MHz. And finally, in the Project Manager tab, I assign a name to the project, set its directory, and choose the toolchain and version. My IDE is IAR Embedded Workbench and its version is 7.8. Everything is fine, so let's generate the code, then open the project. Before programming, we need to verify the connection between the STM32 and the potentiometer. I connected the middle pin of the potentiometer to the PA1 pin of the STM32. The potentiometer acts as a voltage divider, allowing us to measure the divided voltage using the ADC. This setup converts an analog voltage signal ranging from 0 to 3.3 volt into a 12-bit digital value. In my main function, I initialize the ADC using the HAL ADC start function. In the while loop, I read the ADC value with the HAL ADC get value function. The function returns a 12-bit value, which I store in a volatile static integer variable. Let's compile and debug. After running the code, I want to monitor my variable ADC value. To do this, click on View and then select Live Watch. Copy and paste the ADC value variable into Live Watch. Here we can see our ADC value changing. It's not magic. I'm just turning the potentiometer. I'm turning the potentiometer clockwise, and the values I read from the ADC are decreasing. When I turn the potentiometer counterclockwise, the values increase. So far, we have been reading values from the ADC using the polling method, where the HAL ADC get value function is called inside a loop. Alternatively, we can use DMA, direct memory access, to read
ADC values. With DMA, the data transfer happens directly between the ADC and memory, allowing the processor to save time and focus on other tasks. In the ADC parameter settings, enabling DMA continuous request is not directly allowed. To enable it, go to the DMA settings tab and configure the DMA for the ADC. I select circular DMA mode, set the data bit to a word. As you can see here, the direction is peripheral to memory. Now we can go back to parameter settings and enable the DMA continuous requests. Then generate code. We need to declare ADC buffer, an array with 3 elements, as I plan to read multiple ADC channels soon. If you only want to read a single channel, you can declare it as a 1-element array instead. I call the HAL-ADC start DMA function once during this setup to initialize ADC readings using DMA. Since we are using DMA to read the ADC, the processor is not involved in reading the values directly, so the HAL-ADC getValue function is no longer needed inside the loop. So comment these lines. I compile and load the code to see ADC buffer 0. ADC DMA works successfully. We can see our ADC value is changing. Now I need to read multiple channels of ADC with this DMA as I told you before. I enabled ADC in 0, 1 and 2. However, let's ignore ADC in 2 for now and use ADC in 3 instead to demonstrate which ADC channel corresponds to each ADC buffer element. Using LiveWatch, we can observe ADC buffer 0 and 2 are 0 because I connected them to GND. If I connect ADC in 3 to VCC, ADC buffer 2 shows a value close to 4095. Similarly, if I connect ADC in 0 to VCC, ADC buffer 0 is nearly 4095. Finally, if I connect both ADC in 0 and 1 to the same voltage, ADC buffer 0 and 1 display similar values. You can also use ADC with interrupts, but that's all for this video. I hope you found it helpful and learned something new. Feel free to leave any questions or suggestions in the comments below. Thanks for watching and see you in the next video.